Settle in now. Let your body rest where it is. Let your shoulders drop and allow your eyes to close gently. You don't need to follow every detail. Just let the words move past you at a calm, steady pace. Subscribe to catch a new documentary every night and drop a comment telling us where you're tuning in from. By the way, what time is it over there? Okay, just one last question before we get started. What happens when human eyes are finally able to see the universe as it truly is, rather than as it once appeared from a distance? The story begins not with a sudden discovery, but with a quiet limitation. For most of modern astronomy, scientists relied on telescopes that observed the universe in visible light, the same narrow band the human eye can see. This worked well for nearby stars and galaxies, but it left much of the universe hidden. Dust clouds blocked light. Distant objects faded. The earliest galaxies, formed billions of years ago, slipped beyond view as the universe expanded and stretched their light into longer, invisible wavelengths. Astronomers understood this problem clearly. The universe was not dark. Human tools simply could not see far enough into it. The James Webb Space Telescope was designed as a response to that blindness. It was not meant to replace earlier telescopes, but to look where they could not. Its purpose was precise and narrow in definition, yet vast in implication. To observe the universe primarily in infrared light. Infrared light carries information from cold, distant and ancient objects. It passes through dust more easily. It reveals heat rather than brightness. In this range of light, stars form, planets assemble, and the earliest galaxies leave faint signals that travel across time. To understand why this mattered so deeply, scientists had to rethink what seeing meant in space. Light does not arrive instantly. Every image is a record of the past. When astronomers look at the sun, they see it as it was 8 minutes ago. When they observe distant galaxies, they are looking billions of years into the past. The farther away an object is, the older the light becomes. As the universe expands, that light stretches, shifting from visible wavelengths into infrared. This process, known as redshift, is not a theory, but a measured feature of the universe. Without infrared vision, the earliest chapters of cosmic history remain unread. The Webb telescope was built to read those chapters carefully. Its mirror, measuring over 6 meters across, was designed to gather faint infrared light with exceptional sensitivity. Unlike earlier space telescopes, it could not operate near Earth. The planet itself emits heat, and that heat interferes with infrared observations. Even a small change in temperature could overwhelm the signals Webb was meant to detect. To avoid this, the telescope was sent far from Earth, to a gravitational balance point known as the second Lagrange point, or L2. There, it could orbit the Sun alongside Earth, always keeping its instruments shaded and cold. Cold, in this context, is not a metaphor. Webb had to operate at temperatures close to absolute zero. Its sunshield, about the size of a tennis court, blocks sunlight, Earthlight, and moonlight continuously. Each layer of the shield reduces heat further, allowing the telescope's instruments to function with extreme sensitivity. This engineering choice was not optional. Without it, the telescope would see its own warmth rather than the universe beyond. The need for infrared vision was not speculative. Long before Webb launched, astronomers had indirect evidence that something was missing from their models. They knew stars formed inside dense clouds of gas and dust, yet they could rarely observe the process directly. They inferred the presence of exoplanet atmospheres, but could not measure their composition in detail. They suspected that the first galaxies formed quickly after the Big Bang, but existing data lacked clarity. These gaps were not failures of theory, but limits of observation. Webb was built to reduce those limits with precision rather than spectacle. Its instruments were designed to separate light into fine components, allowing scientists to identify specific molecules and elements from distant sources. This technique, called spectroscopy, relies on the fact that atoms and molecules absorb and emit light at exact wavelengths. When infrared light passes through a planet's atmosphere or emerges from a stellar nursery, it carries chemical fingerprints. Webb could detect those fingerprints where no previous telescope could. Before any discovery could be made, however, the telescope itself had to become stable, aligned, and trusted. After launch, months passed without public images. This silence was deliberate. Webb unfolded in space step by step, each movement carefully monitored. Its mirror segments were aligned with nanometer accuracy. Its instruments cooled gradually. Calibration required patience, repetition, and restraint. Scientists resisted the urge to rush toward results. Precision mattered more than speed. This slow beginning reflected the philosophy behind the mission itself. Webb was not designed for quick answers. It was built for deep ones. Every observation would be planned carefully, tested against models, and verified through repeated measurement. The goal was not surprise for its own sake, but clarity. Yet even within this careful framework, scientists understood that seeing farther than ever before carried risk. When observation improves, assumptions are tested. Some hold, others do not. As Webb approached readiness, astronomers prepared for what they might find, knowing preparation could only go so far. Models of the early universe predicted certain timelines, how fast galaxies formed, how massive they could become, how orderly their growth should be. These models were based on the best data available at the time. They were consistent, mathematically sound, and widely accepted. But they were also incomplete, built on partial vision. The moment Webb began returning usable data, the universe did not change. What changed was human access to it. Infrared light that had traveled for billions of years finally reached instruments capable of understanding it. Structures hidden behind dust emerged with clarity. Faint signals grew sharper. Patterns once suggested by theory began to appear directly in images and spectra. This was not a dramatic unveiling. It was a quiet widening of perception. Scientists did not react with disbelief, but with focused attention. Each new dataset was treated cautiously, compared against expectations, and examined for error. The word shock, later used in headlines, did not describe panic or confusion. It described the measured realization that reality contained more structure, complexity, and speed than earlier observations had revealed. At this point in the story, the telescope itself had proven something fundamental. It worked. It saw what it was designed to see. And in doing so, it prepared the ground for discoveries that would follow naturally, not as isolated events, but as a continuous refinement of understanding. The universe had not suddenly changed its behavior. It had simply been observed more completely than before. The story continues by stepping backward in time, long before the telescope ever left Earth, to a period marked by patience, revision, and careful restraint. The James Webb Space Telescope did not appear quickly, and it did not emerge from a single idea or place. It was the result of many years of planning, shaped slowly by limits, mistakes, and changing goals. At the start, there was only a question shared by many scientists. How far back in time could human tools truly see? And what would it take to look even farther? Early discussions began in the late 20th century, when astronomers already knew that visible light telescopes had reached a boundary. They could observe galaxies, stars, and nebulae with great detail. But the earliest stages of the universe remained faint and distant. Light from those times had travelled so long that it no longer appeared bright or sharp. It arrived stretched and weak, mostly outside the range that older telescopes could detect. Scientists understood that to move forward, they needed something larger, colder, and more precise. From the beginning, the idea was ambitious. The telescope would not be a small upgrade. It would require new materials, new methods, and new levels of accuracy. Even small errors could block the mission. Engineers knew this, and so did the scientists who worked with them. Early plans were revised many times, not because of doubt, but because each improvement uncovered new limits. A larger mirror meant more weight. More weight meant harder launch demands. Better sensors meant stricter cooling needs. Every choice created another problem to solve. As the years passed, the project grew beyond one country. The scale was simply too large for a single space agency to handle alone. NASA led the effort, but it was joined by the European Space Agency and the Canadian Space Agency. Each partner brought specific skills and tools. Europe provided the launch vehicle and key instruments. Canada contributed fine guidance systems that allow the telescope to lock onto distant targets with steady accuracy. This shared effort was not symbolic. Without it, the mission could not move forward. Working across borders also meant working across time zones, languages, and systems. Teams had to align not only hardware, but expectations. Designs were reviewed again and again. Parts were tested under extreme conditions. Meetings focused on small details, sometimes for months at a time. Progress was slow, but it was steady. Every delay carried weight, yet rushing was never an option. In space, repair is rarely possible. The telescope would need to work the first time. One of the most difficult challenges was the mirror itself. Webb's mirror is not made from a single piece. It consists of many segments, each shaped and coated with extreme care. Together, they form a surface large enough to collect faint infrared light from the edge of the observable universe. These segments had to fold to fit inside the launch rocket, then unfold and align perfectly once in space. The margin for error was small. A tiny misalignment could blur images or reduce sensitivity. To ensure accuracy, each mirror segment was tested repeatedly on Earth, even though Earth could not fully match space conditions. Engineers cooled the segments to very low temperatures to see how they behaved. Materials expand and shrink when temperatures change. Even a small shift could affect performance. Every adjustment was measured, recorded, and refined. This work did not move quickly, but it moved carefully, step by step. The sun shield posed another major challenge. Unlike mirrors or cameras, it had no moving image to test directly. Its job was simple in description but hard in practice. Block heat at all times. The shield consists of multiple thin layers, each designed to reflect and release heat away from the telescope. When fully deployed, it spans a wide area, far larger than the telescope itself. During launch, it had to be folded tightly, then unfold in space without tearing, twisting, or sticking. This unfolding sequence involved hundreds of small actions. Cables had to tighten, hinges had to open. Tension had to spread evenly across layers. Each step depended on the one before it. Engineers practiced this process again and again on Earth, knowing that space would behave differently. Gravity, air, and friction all change once the telescope leaves the planet. Even so, there was no way to test the entire sequence in real space conditions before launch. Cooling the telescope was another silent but critical problem. Infrared instruments are sensitive to heat. Even the warmth of the telescope itself could interfere with measurements. Webb was designed to cool naturally, without heavy cooling systems that could fail. This required exact placement of parts, precise materials, and constant shade. If the cooling did not work as planned, the telescope would still function, but its most important goals would be lost. As years passed, delays became public. Costs rose. Schedules shifted. Outside observers sometimes questioned whether the mission would ever launch. Inside the teams, however, the focus remained narrow and calm. Each delay allowed another test. Each test reduced risk. The goal was not speed. The goal was success measured over decades, not days. Failure, if it happened, would not be minor. Webb was not designed for repair by astronauts. Its location, far from Earth, made visits impossible with current technology. If a major system failed during deployment, the mission could end before it truly began. This knowledge shaped every decision. Engineers often spoke of single points of failure, parts that had no backup. These parts were examined with special care, redesigned when possible, and tested beyond normal limits. The emotional weight of this risk was real, but it did not lead to panic. Instead, it created a culture of caution. People learned to slow down, to repeat tests, to listen closely when something did not feel right. Problems were not hidden. They were documented and addressed. This process did not make headlines, but it made the telescope stronger. By the time launch approached, the telescope was no longer just a machine. It was the result of many small choices made by thousands of people over many years. Each bolt, cable, and mirror segment carried the record of discussions, failures, corrections, and patience. The telescope was not perfect, but it was prepared. When Webb finally stood ready, folded inside its launch vehicle, the moment felt less like a leap and more like a release. The work on Earth was nearly done. What remained was the quiet transfer of responsibility from human hands to physics itself. Gravity would guide the launch. Motion would unfold the structure. Cold space would cool the instruments. The telescope would either perform as planned or it would not. This long road to launch did not guarantee discovery. It guaranteed only the chance to observe. But that chance had been earned slowly, through restraint and cooperation, through respect for limits rather than defiance of them. In this way, the mission reflected science itself, careful, shared, and built on the acceptance that seeing more clearly requires time. After launch, the telescope did not rush into discovery. It entered a long and careful phase that mattered just as much as the launch itself. In space science, the moment called first light is often misunderstood. It does not mean a clear picture meant for the public. It does not mean a finished image or a scientific result. First light simply means that light from space has reached the instruments and has been recorded in a controlled way. It is a test, not a reveal. For the James Webb Space Telescope, first light was planned to be quiet. Scientists did not expect beauty. They expected proof. Proof that the mirrors could focus light. Proof that the sensors could read faint signals. Proof that data could be stored and sent back to Earth without loss. Every part of this process had to work together. If even one part failed, the telescope would not meet its goals. Before first light could happen, the mirrors had to be aligned. Each mirror segment had been shaped and tested on Earth, but space changes everything. In cold conditions, materials behave differently. The mirror pieces had to move by tiny amounts, guided by motors smaller than a grain of rice. These movements were measured in fractions of a human hair. The goal was simple to describe but hard to achieve. All mirror segments had to act as one smooth surface. Early test images showed stars as many small points instead of one. This was expected. Each mirror segment was still acting alone. Over time, engineers adjusted each segment step by step. With every adjustment, the points of light moved closer together. This process took weeks. It could not be rushed. Each change had to be measured, confirmed, and locked in place before the next one began. During this time, the telescope was already collecting data, but none of it was meant for science yet. The images helped teams understand how light traveled through the system. They revealed small flaws that could be corrected. They showed how temperature shifts affected focus. Every test added confidence. Nothing was shared widely because nothing was final. The instruments themselves also needed calibration. Calibration is the act of teaching a machine how to measure correctly. Sensors respond differently to light based on temperature, age, and design. Scientists expose the instruments to known sources of light, both inside the telescope and from space. By comparing expected values with measured ones, they adjusted settings until the readings matched reality. This process took months, not because it was slow, but because it was careful. Webb was designed to operate for many years. A small mistake made early could affect all future data. Scientists preferred to wait rather than correct problems later. Patience was part of the mission plan from the start. The quiet tension during this phase did not come from fear, but from awareness. Everyone involved knew how much depended on this work. There were no crowds watching live feeds. There were no countdowns. Instead, there were small teams studying graphs, checking numbers, and confirming that systems behaved as expected. Progress was measured in tiny improvements rather than dramatic moments. As calibration continued, the telescope's view sharpened. Stars became points instead of smears. Faint objects emerged from background noise. The instruments began to work together as a single system. At this stage, Webb was still not observing the universe for discovery. It was learning how to observe at all. Only after this long preparation could true first light be declared complete. This did not mark the start of science in a dramatic sense. It marked readiness. The telescope was stable. Its measurements were trusted. Its view was clear. From this point on, data could be shared, compared, and studied with confidence. The months of waiting were not empty time. They were filled with listening to the telescope's behavior, listening to signals from deep space, listening for errors that never came. When scientists finally turned Webb toward its first real targets, they did so knowing that what they would see was not distorted by haste. This moment mattered because it set the tone for everything that followed. Webb would not surprise through speed. It would surprise through clarity. The universe would reveal itself slowly, light by light, measured and confirmed. The telescope was now ready to look far back in time, not with excitement, but with trust. The first images of distant galaxies arrived quietly, almost without notice, yet they carried messages from the universe that had traveled for billions of years. The James Webb Space Telescope was finally looking deep into space, far beyond what previous instruments could reach. Its cameras, sensitive to infrared light, collected faint signals that had been stretched by the expansion of the universe. These signals contained both light and time, showing objects as they were when the universe was very young. Each pixel, each glow, was a record of the past, a small story of formation, growth, and change. Astronomers called these images deep fields, a term first used decades earlier with Hubble. Deep fields are not pictures of a particular galaxy, but of patches of sky observed for long periods. The longer the exposure, the more faint objects appear. Webb's deep fields revealed hundreds of galaxies in a single frame, many of which had never been seen before. What made them remarkable was not only their number, but their brightness, their shape, and their arrangement. These galaxies were small by today's standards, yet some contained mature structures, spiral arms, or dense clusters of stars. They were unexpectedly developed for the time in cosmic history when they were observed. To understand why these images mattered, it is necessary to grasp redshift. Light traveling from distant objects stretches as the universe expands. The farther away an object, the more its light shifts toward longer wavelengths. Visible light can shift into the infrared range, which Webb was designed to detect. Redshift acts like a cosmic clock, allowing astronomers to calculate how long light has been traveling, and therefore how old the observed object is. By measuring the redshift of galaxies in the deep fields, scientists could estimate their distance and their age in a precise way. When the early data was analyzed, scientists noticed something surprising. Some galaxies appeared larger and more complex than existing models, predicted for their age. The universe, according to the accepted understanding, had not had enough time to assemble such structures. The galaxies were mature in a period when astronomers had expected them to be small, faint, and irregular. The discovery did not imply that previous science was wrong, but it suggested that the process of galaxy formation could occur faster or in a different way than previously modeled. These unexpectedly mature galaxies sparked careful attention and analysis. Scientists studied their brightness, their star density, and their mass. They compared these measurements with simulations and earlier observations. Each galaxy carried multiple clues. Some contained heavy elements, which only form through generations of starbirth and death. Some showed tightly bound clusters of stars, implying a level of organization and development that challenged conventional timelines. The images were not spectacular in the sense of flashy colors or dramatic effects. They were significant because they revealed real, measurable properties that required explanation. Webb's observations also showed a variety of shapes and sizes. Irregular forms existed alongside spirals and compact spheres. This diversity suggested that galaxy formation was not a single, uniform process. Environment, local density, and interactions played roles that were only beginning to be understood. Scientists realized that the universe's early period was dynamic and varied, and that previous models had simplified these processes due to the limits of observation. Webb now offered a view without those limits, showing a more complete story. The ability to detect these distant galaxies depended entirely on infrared observation. Light that left these galaxies billions of years ago had been stretched by the universe's expansion into wavelengths invisible to the human eye. Previous telescopes could see only the brightest objects, or those at slightly closer distances. Webb's instruments could detect dimmer red-shifted light, making the faint early universe visible. This capability allowed astronomers to study not just the structure of galaxies, but also their composition, the rate of star formation, and even hints of the dust and gas surrounding them. Each image raised questions about the timeline of cosmic history. If galaxies were more developed than expected so early, what processes could account for this? Were star formation rates higher than models suggested? Did some galaxies grow through mergers faster than anticipated? These questions were not rhetorical, they were measurable. Webb provided data that could be analyzed, modeled, and tested. The telescope did not guess or speculate. It presented evidence. Scientists then had to adjust their understanding to fit the new information. The discovery of mature galaxies in the early universe also affected our sense of scale. Previously, the first billion years after the Big Bang were considered a slow and gradual period of growth. Now, there was evidence of rapid development, showing that the universe was capable of creating complex structures sooner than expected. This revelation did not contradict physics, but it emphasized that the processes governing star and galaxy formation were more efficient or varied than previous observation had allowed scientists to measure. In response to these findings, teams around the world began to re-examine theoretical models. Simulations were adjusted. Predictions were compared against the new data. Some models still matched observations well, but others required significant refinement. Webb's deep field images were a reminder that observation drives understanding, that the universe may follow rules fully consistent with physics, yet reveal complexity that challenges our assumptions. In the quiet of research laboratories and data centers, scientists examined each galaxy in detail. Graphs, spectra, and measurements filled screens. The work was meticulous and slow, emphasizing precision over speed. Each analysis built on the last, creating a gradual layered understanding. The universe revealed itself one careful measurement at a time, and Webb provided the lens for this patient study. These early results would influence more than astronomy alone. They informed our understanding of cosmic chemistry, the formation of the first stars, and the environment in which planets might eventually appear. By showing that mature structures existed so early, the telescope offered insight into the timing and mechanics of processes that ultimately shape entire galaxies and, eventually, systems like our own. As Webb continued to observe, its deep fields expanded. Longer exposures revealed fainter galaxies. Slightly different areas of the sky showed both familiar and new structures. The telescope demonstrated that the universe was both ordered and diverse. No two galaxies were exactly alike, yet patterns could be recognized across billions of light years. This balance of similarity and variation became a foundation for understanding cosmic evolution. Every measurement, every faint point of light was a direct signal from the early universe. The data was factual, tangible, and precise. It did not tell a story through imagination or fiction. It told a story in light, distance, and chemical signature. This was the way science had always spoken, quietly, patiently, and consistently. With Webb, the universe could be read more clearly than ever before, revealing both the unexpected and the inevitable in the same frame. The universe, as observed before Webb, was understood in broad strokes. Scientists had built models of cosmic history that traced the formation of galaxies from the earliest moments after the Big Bang to the present day. According to these models, the universe began as a nearly uniform cloud of energy and particles. Over hundreds of millions of years, small fluctuations in density grew under gravity, pulling matter together to form the first stars. These stars eventually grouped into galaxies, which slowly merged and evolved into larger structures. Observations had matched this general timeline, especially for galaxies seen through the Hubble Space Telescope, which had provided remarkable clarity for the nearer, older universe. But these models always relied on extrapolation. There was an unobservable early period, the first few 100 million years, where the universe was faint and distant. Scientists inferred processes during this time based on theory and indirect evidence. They assumed that galaxy growth would be gradual, that the first galaxies would be small, simple, and irregular. Large, well-formed galaxies would take time to appear, emerging only after many cycles of star formation, mergers, and accumulation of matter. When Webb's early observations arrived, this understanding required adjustment. The telescope revealed galaxies that were surprisingly large, with masses and structures thought impossible for their age. These galaxies contained many stars, some in organized spirals, some with dense cores. Some had already enriched themselves with heavier elements, formed through generations of stellar birth and death. In short, they seemed mature in a period when science expected them to be just beginning. This mismatch created what scientists call tension. In cosmology, tension does not mean panic. It does not indicate error or failure. It simply means that different lines of evidence, or observations versus models, do not align perfectly. Tension signals that our understanding is incomplete. Webb's data added a new layer to this process. Measurements of galaxy size, mass, and composition showed a pattern inconsistent with simple expectations, revealing that the universe may have developed faster in certain areas or through mechanisms that had been underestimated. To resolve this tension, scientists must adapt their models rather than discard them entirely. The laws of physics remain the same, but assumptions about timing, efficiency, and environmental effects can change. Galaxy formation is not uniform across the cosmos. Some regions may have collapsed more quickly, producing larger galaxies earlier. Interactions between matter, dark matter, and energy could accelerate growth. Star formation rates may have been higher in certain early environments. Each factor contributes a piece of the puzzle. Adapting models requires careful calculation. Astronomers take the observed properties of galaxies, brightness, mass, redshift, and chemical composition, and compare them to simulations. If discrepancies appear, they adjust input variables, test alternative mechanisms, and repeat simulations to see if the results converge with reality. This is an iterative process. One adjustment may solve a problem in one observation, but create a mismatch elsewhere. Over time, the model becomes more robust, encompassing both old observations and the new. more detailed data from Webb. The realization that some galaxies were too large too soon did not overturn science. Instead, it highlighted gaps in knowledge and offered a chance to refine predictions. Scientists considered multiple explanations. Some galaxies may have formed stars at an unusually rapid rate, while others may have merged frequently with nearby structures. Observations of dense gas clouds, chemical abundances, and star formation regions provided clues about which scenarios were plausible. Each new measurement narrowed the possibilities without forcing assumptions to extremes. This process illustrates a principle central to scientific investigation. Understanding evolves with evidence. Models are never complete. They are always provisional, designed to describe the universe as accurately as possible with current knowledge. When new data arrives, models must flex, accommodating unexpected findings while remaining consistent with known physical laws. Webb provided such data in abundance. Its high-resolution images and spectra offered both confirmation of some predictions and challenges to others, prompting re-evaluation at every level. The adaptation of models also revealed the universe's complexity. Early galaxies are not all identical. Some are small and irregular, confirming earlier expectations. Others are massive and organized, exceeding predicted sizes. This variety shows that the universe operates under general principles, but allows for diverse outcomes depending on local conditions, cosmic environment, and the interplay of forces. No single galaxy defines the rule. Patterns emerge only when multiple observations are combined. Understanding cosmic timelines also affects our perception of the universe's scale. If galaxies formed more rapidly than anticipated, the early universe may have been richer in structure, star formation, and chemical complexity. The first billion years, once imagined as quiet and slow, now appear dynamic and varied. Processes that were thought gradual may have occurred in bursts. Interactions between matter and energy may have accelerated evolution. Each revelation emphasizes that timelines are not rigid, but flexible, responding to the interplay of fundamental forces. Scientists now approach these early galaxies with both curiosity and caution. They know that a single observation cannot redefine understanding entirely, yet the weight of multiple images, spectra, and measurements gradually reshapes the picture. Every data point is assessed, verified, and placed within the broader context of cosmic history. This deliberate approach ensures that conclusions remain grounded in evidence rather than imagination. As research continues, models of galaxy formation and growth will incorporate these findings. Adjustments may include higher star formation efficiency, more frequent early mergers, or faster chemical enrichment than previously assumed. By refining models rather than abandoning them, scientists maintain a coherent understanding of cosmic evolution, capable of explaining both early and later stages of the universe. The tension revealed by Webb is not a failure, but an invitation to look closer, measure carefully, and deepen comprehension. The early galaxies observed by Webb thus serve as both evidence and teacher. They demonstrate that the universe can surprise, yet do so in a way consistent with its own laws. They remind us that the past is accessible only through patient observation, and that careful measurement allows us to trace development across billions of years. In this context, cosmic timelines are not fixed schedules, but evolving narratives, continuously rewritten by new discoveries. As Webb turned its gaze closer to home, it began to study worlds beyond our solar system. These distant planets, called exoplanets, orbit stars far away, each carrying its own mysteries. Unlike stars, planets do not shine on their own. They reflect or absorb the light of their host stars, which makes them faint and difficult to detect. Webb does not see these planets directly in most cases. Instead, it observes the light that passes through or is reflected by their atmospheres. This light carries subtle patterns, tiny signatures that reveal the chemical makeup of each world. The method Webb uses is called spectroscopy. When light passes through a planet's atmosphere, molecules absorb certain wavelengths while letting others pass. Each chemical, like water, carbon dioxide, or methane, leaves a distinct pattern. By spreading the light into a spectrum and studying these absorption lines, scientists can determine which molecules are present, in what amounts, and sometimes even how they are distributed. It is a quiet form of measurement, precise and patient, relying on careful detection of faint differences in color and intensity. Previous telescopes had detected some of these chemicals in exoplanet atmospheres, but with limited detail. Webb's instruments, with high sensitivity to infrared light, provide a far more refined view. They can detect weaker signals, distinguish overlapping molecular features, and observe multiple layers of an atmosphere. This allows scientists to measure temperature variations, identify clouds or haze, and infer wind patterns in some cases. Each spectrum is a map, a subtle reading of a planet's composition and climate, formed entirely from light that has traveled hundreds or thousands of years to reach Earth. Among the molecules Webb has detected, water vapor is especially significant. Water is a common byproduct of chemical reactions in planetary atmospheres, and it affects climate, weather, and the potential for supporting life. Carbon dioxide is also critical, as it helps regulate temperature through greenhouse effects. Methane, meanwhile, can be produced by both chemical and biological processes. The detection of these molecules does not mean life exists, but it provides essential clues about the physical and chemical processes shaping each world. Webb's observations have revealed these molecules in unprecedented detail. Scientists can now distinguish not only their presence, but also their relative abundance. In some planets, water is concentrated in lower layers. In others, methane dominates higher layers. Clouds and haze can obscure certain molecules, but the telescope can often see through or around these obstructions using infrared light. This level of detail surpasses previous measurements, offering a richer, more accurate picture of distant atmospheres than any other instrument before it. With this new information, scientists can begin to compare planets in systematic ways. Some are hot gas giants close to their stars, their atmospheres dominated by thick hydrogen and helium with traces of heavier molecules. Others are smaller, rocky worlds, where water vapor or carbon dioxide may exist in moderate amounts. Each observation adds to a growing understanding of how planetary atmospheres form and evolve, how temperature and stellar radiation affect composition, and how planets differ across the galaxy. The question of habitability often arises when discussing these findings. Habitability does not mean a planet is inhabited. It does not guarantee life. Rather, it indicates whether conditions might allow life as we understand it to exist. Webb's detection of water vapor, carbon dioxide, and methane informs this assessment. Water suggests the potential for liquid, carbon dioxide affects temperature, and methane indicates chemical activity. Together, These clues help scientists determine which planets warrant further study without jumping to conclusions. Some exoplanets discovered by Webb challenge expectations. Worlds once considered too close to their stars may retain thick atmospheres with complex chemistry, while distant gas giants show signs of chemical layering that was previously only theorized. Each observation adds subtlety to the concept of habitability. It is not a binary measure. It is a spectrum informed by composition, temperature, radiation, and atmospheric dynamics. Webb allows scientists to measure many points on this spectrum with clarity. Webb also helps refine models of planetary evolution. By studying a wide variety of exoplanets, scientists can identify trends in atmospheric composition relative to age, size, and stellar type. For example, planets orbiting young stars often show more active chemistry, while older planets may have more stable atmospheres. These patterns reveal how planets change over time and how their atmospheres interact with light and radiation. Each data point is a small piece of a larger cosmic puzzle. This approach emphasizes observation over speculation. Webb does not decide which worlds are Earth-like in the way science fiction imagines. It measures molecules, temperature, and atmospheric structure. The telescope allows scientists to observe patterns, make calculations, and generate reliable predictions about chemical and physical conditions. In doing so, it provides a foundation for further studies, both with Webb and with future telescopes designed to probe smaller and fainter worlds. Even small details in the spectra can carry large implications. Slight differences in water concentration can indicate cloud cover or rainfall processes. Variations in methane levels can suggest photochemical reactions or circulation patterns. Each measurement must be interpreted carefully, considering the limitations of distance, faintness, and instrument sensitivity. Yet, the fact that these measurements are now possible represents a step forward in understanding planets beyond our solar system. Webb's work in exoplanet atmospheres also complements its study of galaxies and stars. Observing chemical processes on small planets informs understanding of larger cosmic systems. Molecules form in stars and stellar nurseries, travel through space, and ultimately contribute to planetary atmospheres. The telescope connects these scales, from the faint glow of a distant galaxy to the subtle absorption line in an exoplanet's spectrum. This continuity reinforces the broader scientific picture that Webb is gradually revealing. A universe governed by consistent physical laws, observable in detail from the largest structures to the smallest planets. In this way, the telescope's observations of exoplanets are not isolated curiosities. They are part of a continuous record of cosmic evolution. By measuring molecules, temperatures, and atmospheres, scientists trace the pathways of matter and energy across space and time. Each world adds to the story, helping to explain how planets form, evolve, and maintain conditions that may someday support life, at least in principle. Webb's view of the universe is not limited to distant galaxies or exoplanets. It also looks closely at the regions where stars are born. These areas, called stellar nurseries, are often dense clouds of gas and dust. In visible light, they can appear dark or obscured, hiding the processes within. Infrared light, however, passes through much of the dust, revealing the glowing cores where new stars are forming. Webb's instruments can see these cores in detail, allowing scientists to study the earliest stages of star development. To understand the composition of these nurseries, Webb relies on spectroscopy. This technique spreads light into its component colors, like a rainbow, but at precise wavelengths that reveal the fingerprints of molecules and atoms. Each chemical absorbs or emits light at specific wavelengths, creating patterns that are measurable even from billions of light years away. By analyzing these patterns, scientists can identify elements like hydrogen, oxygen, carbon, and more complex molecules like water, ammonia, or methane. In this way, light itself becomes a messenger, carrying the secrets of chemistry across vast distances. When Webb looks at stellar nurseries, it often sees more than just hydrogen and helium, the most abundant elements in the universe. It detects molecules that are the building blocks of stars, planets, and even potential life. Water vapor, carbon compounds, and simple organic molecules appear in concentrations that had not been observed in such clarity before. Each detection provides information about temperature, density, and chemical reactions occurring in the cloud. These insights are not dramatic in the way a movie scene might be, but they are rich in detail and deeply informative, revealing the underlying processes shaping the universe. One striking finding is the presence of complex molecules in regions where stars and planets are forming. Simple molecules like hydrogen combine under heat and pressure to form more complex compounds. Dust grains serve as scaffolds, allowing atoms to bond and molecules to grow. Webb can detect these molecules through subtle absorption and emission features in the infrared spectrum. This ability marks a significant advance over earlier telescopes, which often could only identify the simplest or most abundant molecules. Now, scientists can map chemical diversity, observe interactions, and track the evolution of matter within stellar nurseries. These chemical discoveries illuminate how stars form. In dense regions, gas collapses under gravity, forming protostars. The chemical composition of the surrounding cloud influences temperature, pressure, and the rate of collapse. Certain molecules help cool the cloud by radiating heat into space, allowing gravitational collapse to continue. Others absorb energy, creating complex feedback that regulates star growth. Webb allows scientists to observe these processes indirectly through the light emitted and absorbed by specific molecules. This information provides a more complete picture of the physical and chemical environment shaping stars. Planet formation is also tied to these observations. The disks of gas and dust surrounding young stars, called protoplanetary disks, contain the ingredients for planets. Webb can detect molecules within these disks, tracking water, carbon compounds, and organics that may eventually become part of planets. The distribution of these molecules informs models of planet formation, showing how material moves inward or outward, how solids condense, and how early atmospheres may develop. Each spectrum, each line in the data, represents a tangible step in the story of planetary birth. The clarity of Webb's spectroscopy is unprecedented. It allows scientists to distinguish overlapping molecular signals, separate layers within disks, and measure relative abundances. Previous observations often blended multiple signals, creating uncertainty. Webb's precision removes much of this ambiguity, revealing the true diversity and complexity of chemical environments. Scientists can now compare stellar nurseries across regions and ages, observing how chemistry evolves from one cloud to another and across time. This chemical mapping also has implications for understanding potential habitability. Molecules detected in these regions, like water and simple organics, are ingredients necessary for life as we know it. Their presence does not imply life exists, but it indicates that the raw materials for life are widespread in the galaxy. Webb thus provides a broader context, linking the formation of stars, the birth of planets, and the potential for life in a coherent observational framework. Chemistry becomes a bridge connecting physical processes with cosmic evolution. Each observation of a stellar nursery tells a story of matter in motion. Atoms collide, bonds form and break, and energy flows through the cloud. Dust grains accumulate, and gravity shapes structures that will eventually become stars and planets. The telescope does not dramatize these events, but it allows scientists to witness them in real detail, tracing the interplay between physics and chemistry over millions of years. The narrative is written in starlight, slow, subtle, and precise. Webb's observations also refine theoretical models. Chemical abundances and distributions inform simulations of star and planet formation. For example, measuring water vapor in different regions shows how cooling and heating occur, affecting the size and mass of forming stars. Tracking carbon-bearing molecules helps scientists understand the potential for forming rocky planets and organic compounds. Each measurement adds constraints, making models more accurate and predictions more reliable. In this way, the telescope turns light into a language. By carefully decoding the signals, scientists reconstruct the processes that build stars, shape planetary systems, and prepare the ingredients for life. Webb provides evidence, not speculation, allowing a factual understanding of how the universe organizes itself at small scales within stellar nurseries. It is a slow, detailed process, but one that gradually reveals patterns and structures hidden from view before. The telescope's findings demonstrate continuity across scales. Molecules in a small cloud are linked to the stars they form, which in turn influence their surrounding space, contributing to the growth of galaxies. Chemistry is not confined to a single location. It travels, interacts, and evolves, shaping the universe in ways that Webb can now observe directly. These observations connect microscopic processes to large cosmic structures, emphasizing the coherence of physical laws across space and time. Through its spectroscopy, Webb shows that complexity arises naturally from simple ingredients. Hydrogen and helium provide the baseline. Through interactions, collisions, and energy exchanges, these atoms form increasingly complex molecules. Dust grains facilitate growth. Radiation and temperature variations create gradients that drive chemical reactions. Over time, this complexity leads to stars, planets, and the potential for life. Webb allows scientists to witness these stages with clarity, confirming models while also revealing new subtleties previously hidden. Even though space is mostly empty, vast clouds of dust obscure much of what lies within it. Dust grains, tiny as smoke particles, block and scatter visible light. In the past, these clouds hid the most active regions of star formation, leaving astronomers to guess at what occurred inside. Nebulae, dense clouds of gas and dust, often appeared as dark smudges or faintly glowing shapes in telescopes. Their internal structures were mostly invisible. It was as though the universe kept its secrets under layers of shadow, waiting for the right light to reveal them. Infrared light, longer in wavelength than visible light, interacts differently with dust. It can pass through dense clouds with less scattering, allowing hidden regions to become visible. This is why Webb's infrared capability is crucial. By observing in infrared, the telescope can peer inside dusty nebulae, mapping the distribution of gas, dust, and forming stars. Light that would otherwise be blocked carries information about processes occurring deep inside the cloud. The telescope reads this light carefully, separating faint signals from the background and revealing intricate patterns that were once invisible. In these observations, nebulae become complex landscapes. Dust lanes twist and wind through glowing gas, forming channels where stars gather. Dense pockets of material collapse under gravity, creating protostars that are often surrounded by rotating disks of gas and dust. Webb reveals these disks as faint rings and shadows, marking where planets may eventually form. Some protostars are still faint, dimly glowing in infrared light, while others are brightening as they gather mass. By imaging these regions, scientists see stages of star formation that were previously only inferred from models. One of the most striking revelations is the variety of structures within a single nebula. Filaments of gas stretch across light years, dense knots mark sites of future stars, and cavities appear where young stars have begun to push away surrounding material. These features are not static. They change over time as gravity, pressure, and radiation interact. Webb can capture these details with unprecedented clarity, showing the complexity of star-forming regions and the dynamic processes that shape them. Infrared observations also reveal temperature differences within clouds. Cooler regions appear differently than warmer ones, highlighting areas where gas is collapsing versus regions heated by nearby stars. This helps scientists understand not only where stars are forming, but also how efficiently the material is transforming into new stellar bodies. Webb's data allows for precise measurement of these gradients, mapping both the physical and chemical conditions within nebulae. Another key insight comes from observing clusters of stars forming together. Webb can detect young stars embedded in dust, sometimes in groups that span light years. These clusters reveal interactions between stars, showing how their gravity, radiation, and winds influence the surrounding environment. Some stars carve out cavities in the cloud, pushing dust aside, while others remain hidden in dense regions. The telescope captures both the brightness of emerging stars and the shadows of materials still collapsing around them. By comparing images over time, scientists can observe subtle changes in these regions. Dust moves, gas flows, and young stars grow brighter as they accrete mass. Though these processes take thousands of years, the telescope's precision allows for tracking of small-scale changes across the nebula. This is a form of real-time observation, in the sense that changes can be measured and documented rather than being inferred solely from theory. Webb also detects variations in chemical composition across nebulae. Certain molecules are concentrated in cold, dense regions, while others appear near warmer, exposed areas. This spatial mapping provides clues about the progression of star formation and the movement of material within clouds. Scientists can determine where cooling allows collapse, where radiation slows formation, and how the balance of forces shapes the structure of the cloud. Dust itself becomes a source of insight. Its distribution, density, and composition affect both light and the dynamics of the cloud. Infrared observations can distinguish between different types of dust grains, their sizes, and how they interact with surrounding gas. This information informs models of planet formation, since dust is the material from which solid bodies eventually grow. Webb thus connects the hidden structure of nebulae to the broader narrative of star and planet birth. Even in regions previously considered dark and featureless, Webb finds intricate patterns. Shadows reveal cavities and filaments, glowing regions mark the hottest zones, and subtle shifts in brightness hint at motion. Every observation provides data that builds a detailed picture of star formation as it occurs, rather than relying solely on extrapolation. The telescope's ability to see through dust transforms what was once invisible into measurable reality. Through these images, the universe appears as a dynamic, layered environment. Dust and gas are not obstacles but participants, shaping where stars form, how material moves, and the ultimate architecture of stellar nurseries. Webb captures both the quiet accumulation of matter and the energetic interactions that disperse material, offering a full view of processes once hidden. Scientists can now study the life cycle of stars from their first moments of formation, through growth to emergence from the dusty womb that once concealed them. When the first images and data from Webb arrived, scientists were not shocked in the sense of disbelief or panic. Shocked in this context meant surprise at how much detail and clarity the telescope provided, revealing structures and patterns that had been invisible until now. Researchers quickly realized that some observations did not fit neatly into existing models. Galaxies appeared more developed than expected. Star-forming regions showed complexities that exceeded prior simulations. Exoplanet atmospheres contained unexpected chemical ratios. Each discovery added depth and nuance, prompting careful reflection rather than alarm. The first step after receiving surprising data is verification. Every image, spectrum, and measurement is examined in detail. Scientists check for errors in instrumentation, data transmission, and analysis. They confirm that the signal is real, not a glitch or artifact caused by the telescope, the detectors, or the processing software. Multiple teams often work independently, using different methods to reproduce results. Only when several independent analyses converge do researchers begin to consider the observations as reliable evidence. This process is slow, deliberate, and essential to maintaining scientific rigor. Peer review is another critical part of this verification. Before results are published, scientists submit their findings to other experts in the field. These reviewers scrutinize methods, assumptions, and interpretations. They look for errors, alternative explanations, or overlooked factors. The process may result in revisions, clarifications, or further tests. Peer review ensures that conclusions are grounded in solid evidence and reasoning, rather than personal interpretation or wishful thinking. Webb's discoveries underwent this careful scrutiny, producing results that were both surprising and credible. Healthy scientific uncertainty plays a central role during this phase. Scientists recognize that not every detail is immediately understood. Some observations raise more questions than answers, but this is a normal and necessary part of research. Uncertainty motivates further study, additional observations, and refinement of models. It is not a weakness, it is a recognition that the universe is complex and understanding develops over time. Webb's data illustrates this principle. Each discovery contains a mixture of clarity and ambiguity, inviting scientists to explore deeper rather than offering definitive conclusions immediately. As researchers processed Webb's early findings, they also began to adjust their models. Models of galaxy formation, star birth, and planetary atmospheres were tested against the new evidence. In cases where data contradicted expectations, scientists explored alternative explanations. For example, some early galaxies seemed larger or more mature than models predicted. Teams examined the rate of star formation, the efficiency of mergers, and the distribution of matter in simulations. Adjustments were made where necessary, refining models to accommodate the new observations without discarding the well-established physical principles underlying them. This iterative process is a hallmark of science. Observations lead to analysis, which leads to refinement of understanding. Surprising results are not dismissed. They are incorporated into a growing framework of knowledge. Over time, models become more accurate, more predictive, and more complete. Webb's high-resolution data accelerates this process, providing measurements and images of unprecedented precision. Scientists can now test assumptions that were previously theoretical, filling gaps in knowledge with direct evidence rather than inference alone. The community of scientists engaged with Webb's discoveries shares a balance of excitement and caution. The excitement comes from seeing the universe in new ways, with details never before visible. The caution comes from understanding the complexity of interpretation. Every data point is carefully contextualized, compared with prior observations, and evaluated within theoretical frameworks. The result is a disciplined yet dynamic approach, where models evolve naturally as new evidence accumulates. Adjustments made in response to Webb's data often involve reconsidering timelines and processes. For instance, the unexpected maturity of early galaxies suggested that star formation and galaxy growth could occur more rapidly in certain conditions. Researchers studied the effects of environmental factors, gravitational interactions, and early cosmic chemistry to explain these observations. Each adjustment is supported by evidence, verified through multiple methods and integrated with existing knowledge. This careful approach ensures that new insights enhance, rather than destabilize, the broader understanding of cosmic evolution. Even when results are surprising, science remains collaborative. Teams share data, discuss interpretations, and test competing hypotheses. International collaboration strengthens verification, as independent observations and analyses confirm or challenge initial findings. Webb's mission benefits from this collaborative framework. NASA, ESA, CSA, and other partners contribute expertise, ensuring that discoveries are understood from multiple perspectives. This collective effort reduces bias, increases reliability, and fosters a comprehensive understanding of the data. Importantly, surprises from Webb do not invalidate prior science. Instead, they provide opportunities to refine it. Models that predicted certain outcomes remain valid within their parameters. New observations simply expand the range of known behavior. Early galaxies that appear unusually mature, stellar nurseries with intricate chemical patterns, and exoplanet atmospheres with unexpected compositions. All these findings enhance knowledge. They provide constraints that guide future research, clarify uncertainties, and focus attention on areas needing further study. The response to Webb's discoveries also highlights a key principle. Evidence drives understanding, not expectation. Scientists do not reject data that contradicts their models. They use it to improve models, deepen analysis, and explore new hypotheses. Surprising observations are instructive rather than alarming, providing lessons about the complexity and variety of the universe. Webb's early results exemplify this process, demonstrating how careful observation leads to measured adjustment and refined comprehension. Over time, the initial surprise of Webb's findings transitions into a steady accumulation of knowledge. Observations that once seemed shocking become integrated into a broader, coherent picture. Scientists develop new frameworks for interpreting galaxy formation, starbirth, and planetary chemistry. Each discovery contributes to this framework, reinforcing the iterative nature of science. Observe, analyze, adjust, and understand. Webb's mission exemplifies this cycle, providing data that continuously informs and enhances cosmic understanding. Through careful verification, peer review, and model adjustment, scientists build confidence in their conclusions. Uncertainty is acknowledged and addressed, not ignored. Webb's contributions illustrate the value of patience, rigor, and collaboration. By responding thoughtfully to surprises, the scientific community ensures that knowledge grows steadily, accurately, and meaningfully. Each insight strengthens understanding, shaping a more precise view of the universe across time and space. Webb's gaze extends far beyond individual stars and galaxies, reaching into the vast architecture of the universe itself. At the largest scales, galaxies are not distributed randomly. Instead, they form a network of filaments and clusters, connected in patterns that stretch across billions of light years. Between these structures lie immense voids, nearly empty spaces where few galaxies exist. This intricate arrangement is often called the cosmic web. For decades, astronomers inferred its existence through surveys of galaxy positions and redshifts. But Webb allows a more detailed and precise view than ever before. Using its infrared instruments, Webb can detect galaxies that are faint, distant, or obscured by dust, revealing structures that were previously invisible. Long exposures across carefully chosen regions of the sky show how galaxies are distributed, not as isolated points, but as nodes and strands forming continuous patterns. Filaments of galaxies extend across enormous distances, connecting clusters that contain thousands of galaxies each. These filaments trace the flow of matter, providing a snapshot of how the universe is organized on the grandest scales. Within these filaments, galaxies do not exist independently. They interact gravitationally, influencing one another's motion, growth, and evolution. Clusters form where filaments intersect, regions dense with matter and activity. These intersections are sites of galaxy mergers, starburst activity, and the accumulation of gas and dust. Webb's observations capture both the individual galaxies and the larger structures they inhabit, showing how small-scale processes contribute to large-scale patterns. The telescope provides the resolution and sensitivity needed to map faint galaxies that would otherwise be missed, completing the picture of cosmic architecture. Void regions, by contrast, are nearly empty, containing only a few isolated galaxies. These vast spaces provide contrast to the filaments and clusters, emphasizing the uneven distribution of matter in the universe. Studying voids is important because their existence and properties offer clues about the overall density of matter, including dark matter, which cannot be observed directly. Webb's ability to detect faint galaxies, even in low-density regions, allows scientists to measure the distribution of both ordinary and unseen matter, revealing how gravity and expansion shape the cosmos. The cosmic web is a direct consequence of the way matter clumps under gravity over billions of years. Small fluctuations in the early universe's density grew, drawing in gas, dust, and dark matter. Over time, these accumulations formed filaments, clusters, and voids. Webb provides detailed evidence of this process by showing the positions, brightness, and mass of countless galaxies. By observing these structures at different distances, and thus at different times in cosmic history, astronomers can trace how the Webb developed over billions of years, confirming theoretical models with direct observation. One of the striking aspects of these images is the connectivity between galaxies. Individual galaxies, often studied in isolation, are now seen as part of a network, their evolution influenced by their position within the Webb. Galaxies near dense clusters may experience frequent mergers, while those in the filaments may grow more steadily, and those isolated in voids may evolve slowly. Webb's data allows scientists to measure environmental effects on galaxy formation, providing a comprehensive view of cosmic evolution that combines local processes with large-scale structure. Infrared observations are particularly valuable for mapping the cosmic web at high redshifts. Light from the earliest galaxies is stretched into the infrared by the expansion of the universe. Webb can detect these distant objects, tracing filaments that existed when the universe was only a fraction of its current age. Observing the cosmic web at different epochs reveals how structures grew and evolved, and whether early clustering of galaxies matches predictions from simulations. These measurements refine our understanding of the timing and pace of cosmic evolution, showing that the Webb's large-scale pattern emerged early and became increasingly complex over time. Webb also provides information about the mass distribution within clusters and filaments. By measuring the light from galaxies and the effects of gravity on surrounding matter, scientists can estimate where mass is concentrated, including dark matter. Dark matter does not emit light, but it exerts gravitational influence, shaping the structure of the Webb. Filaments are thought to trace regions of higher dark matter density, guiding the formation of galaxies and clusters along these invisible pathways. Webb's detailed mapping of visible matter, combined with gravitational models, illuminates the hidden scaffolding of the universe. In addition to mapping galaxies, Webb reveals subtle differences in their properties depending on location within the Webb. Galaxies in clusters often have less gas, as interactions strip material away, while those in filaments may retain more. Star formation rates, chemical abundances, and galaxy shapes all vary with environment. Observing these trends across thousands of galaxies allows scientists to understand how local conditions and large-scale structure work together to influence evolution. Webb's data provides a coherent, measurable link between the microscopic processes inside galaxies and the macroscopic structure of the cosmos. By creating detailed maps of filaments, voids, and clusters, Webb helps answer fundamental questions about the universe's composition. It shows how ordinary matter, dark matter, and dark energy interact to produce the large-scale patterns we see today. Comparing nearby structures to those at great distances allows astronomers to reconstruct the growth of the cosmic web, confirming predictions about gravitational collapse, expansion, and the influence of dark matter. Each filament and void tells a part of the story, contributing to a comprehensive understanding of cosmic architecture. In these observations, the universe appears both ordered and dynamic. Filaments stretch across unimaginable distances, yet within them, galaxies form, interact, and change over time. Clusters contain thousands of individual systems, each with its own history. Voids are not empty of significance. They define boundaries and contrast, emphasizing the uneven distribution of matter. Webb captures all of this in infrared light, revealing structures that are otherwise invisible, showing how the universe is woven together at scales far beyond the imagination. Webb's mapping of the cosmic web also informs other areas of astronomy. Understanding the large-scale distribution of matter helps interpret observations of galaxy formation, star formation, and planetary systems. It provides context for chemical enrichment, starburst activity, and the growth of supermassive black holes. By connecting individual discoveries to the broader structure of the universe, Webb allows scientists to see patterns and relationships that were previously hidden. This holistic view strengthens models and offers a foundation for future exploration. Through this process, scientists gain both precision and perspective. They can count galaxies, measure their properties, and map their locations, but they also see the larger patterns that govern cosmic evolution. Webb turns what was once a simple catalogue of galaxies into a rich, interconnected story of matter, energy, and structure. Each observation builds a more complete picture of how the universe arranges itself across billions of light years, connecting the smallest and largest scales in a coherent framework. The light that reaches Webb from distant galaxies is, in essence, a message from the past. Because light travels at a finite speed, observing a galaxy billions of light years away means seeing it as it existed billions of years ago. Every photon captured by Webb carries information about the conditions, chemistry, and activity of that galaxy at the moment it began its journey. In this way, the telescope acts as a time machine, allowing scientists to study different epochs of the universe by observing light emitted at varying distances. Each observation is a glimpse into a specific era, a chapter in the long history of cosmic evolution. Early stars and quasars, the most luminous objects in the young universe, are of particular interest. The first stars, composed mostly of hydrogen and helium, formed within a few 100 million years after the Big Bang. Their light is stretched or redshifted by the expansion of the universe, shifting it from visible to infrared wavelengths. Webb, sensitive to this infrared light, can detect these ancient stars, measuring their brightness, temperature, and chemical composition. Similarly, quasars, supermassive black holes accreting matter at enormous rates, emit intense radiation. Webb's instruments capture their spectra, revealing details about their surrounding gas and the processes fueling their immense luminosity. By observing light from multiple epochs, scientists can construct a layered picture of cosmic evolution. Nearby galaxies show relatively recent conditions, while distant galaxies reveal the universe in its infancy. Each layer adds depth to our understanding, illustrating how galaxies grow, how star formation changes over time, and how the chemical composition of matter evolves. Webb allows these layers to be observed systematically, enabling comparisons across billions of years and offering insights into the pace and sequence of cosmic events. Repeated imaging and long-term monitoring enhance this understanding. Some phenomena change over time, such as variable stars, transient events, or the growth of quasar activity. By revisiting the same regions of the sky, Webb captures subtle variations, measuring how brightness, structure, or chemical features evolve. This continuity is essential for distinguishing temporary anomalies from persistent patterns. It allows scientists to confirm trends, refine models, and track processes that unfold on timescales of years, decades, or even longer. Layered observations also illuminate interactions between objects. A galaxy forming at high redshift may show signs of mergers, inflows of gas, or starburst activity. By comparing its properties to nearby galaxies, scientists can trace how such interactions shape growth and evolution. Patterns emerge, revealing the role of environment, mass, and chemistry in determining a galaxy's trajectory. Webb provides the resolution and sensitivity necessary to measure these factors across time, linking early structures to those observed in the present universe. The telescope's ability to observe faint light is crucial for detecting the earliest structures. Early stars and galaxies are small, dim, and often embedded in clouds of gas. Infrared light penetrates dust, allowing Webb to reveal these hidden objects. Each detection adds to a growing census of the young universe, showing how the first luminous structures emerged from the primordial darkness. Scientists can measure star formation rates, chemical abundances, and mass distributions, constructing a more complete understanding of the universe's formative periods. Observing quasars and active galactic nuclei provides complementary insight. These energetic objects influence their surroundings, shaping star formation and distributing heavy elements. Webb captures their light in fine detail, revealing both the central black hole's activity and the impact on the host galaxy. By observing quasars at different distances, scientists track their evolution and role in cosmic history. This perspective allows researchers to understand feedback processes and their effect on subsequent generations of stars and galaxies. Each epoch revealed by Webb also contributes to understanding rayonization, a critical period when the universe transitioned from neutral to ionized hydrogen. Light from the first stars and galaxies provides evidence of this phase, showing when and how the intergalactic medium became transparent to ultraviolet radiation. Observations of faint galaxies and distant quasars indicate the timeline and pace of rayonization, clarifying a period that was previously accessible only through indirect inference. Webb's data therefore provides direct evidence of key transitions in the universe's early history. Long-term monitoring and repeated imaging serve another purpose. They increase the statistical significance of findings. Single observations may detect rare objects or anomalies, but repeated surveys confirm patterns, reduce errors, and identify consistent trends. Webb can revisit regions multiple times, building a comprehensive record of light from different distances and epochs. This cumulative approach strengthens confidence in conclusions and allows scientists to detect subtle effects that might otherwise be overlooked. By treating light as a chronological record, astronomers transform observations into a timeline of cosmic events. Each photon carries a timestamp, marking when it was emitted. Webb's instruments capture this information with precision, allowing scientists to reconstruct the sequence of star formation, galaxy growth, and chemical evolution. Layering these observations creates a multidimensional map of the universe's history, linking distant epochs to the conditions we observe in the modern cosmos. The concept of time capsules extends even to nearby galaxies. Though closer objects emit light that reached Earth more recently, their detailed observation provides a reference for comparing early structures to those in the local universe. By combining information across distances, scientists understand both continuity and change in cosmic evolution, identifying patterns that persist and processes that vary with time and environment. Ultimately, Webb's layered observations reveal the universe as a dynamic, evolving system. Its light shows how structures emerge, grow, and interact over billions of years. Each epoch adds context for the next, demonstrating how small, early galaxies eventually merge into larger systems, how stars recycle material into new generations, and how chemical enrichment proceeds across cosmic time. This continuous record allows science to move from snapshots to a coherent narrative of the universe's history. As Webb's observations of exoplanets accumulated, scientists began to notice patterns that were both fascinating and puzzling. Some planets did not orbit their stars in simple circular paths, as models had predicted. Instead, they followed elongated, eccentric orbits, sometimes tilted at angles that seemed unusual compared with their sibling planets. These orbital configurations revealed a variety of dynamical histories, hinting at interactions, migrations, and gravitational effects that had been underestimated in earlier models. Webb's high-precision infrared measurements allowed researchers to detect these subtle shifts and alignments with unprecedented clarity. Multi-planet systems proved especially interesting. While some systems resembled our own, with planets roughly aligned in a flat plane, others displayed dramatic tilts and irregular spacing. In several cases, outer planets were found much farther from their stars than expected, while inner planets were unusually close, creating contrasts that challenged classical theories of planetary system formation. Webb's instruments could measure the light filtered through or emitted by these planets, determining their sizes, atmospheric compositions, and relative positions. These details revealed a diversity far richer than previously imagined, highlighting the complexity of planetary dynamics. In some systems, planets appeared to have shifted over time, migrating inward or outward due to gravitational interactions with other planets or the protoplanetary disk from which they formed. Webb's repeated observations provided evidence of these movements indirectly, through changes in orbital timing and atmospheric characteristics. Scientists could compare systems of different ages, identifying patterns that suggested certain evolutionary pathways are common, while others are rare or unusual. This information helps refine theoretical models, showing which mechanisms of migration, resonance, and interaction are most influential in shaping planetary systems. Unusual exoplanets also challenged expectations about composition and size. Some planets, larger than expected for their distance from the star, suggested dense cores or extended gaseous envelopes. Others appeared smaller or less massive than models predicted, indicating variations in material accumulation or loss. Webb's infrared spectroscopy allowed researchers to measure atmospheric molecules, detecting water, carbon compounds, and trace elements that provide clues about formation processes. By analyzing these chemical signatures in relation to orbital characteristics, scientists gained a more complete understanding of how planets evolve in diverse environments. One particularly surprising discovery involved systems where planets orbit in opposite directions, or with significant tilts relative to one another. These configurations suggest complex histories, perhaps involving early gravitational interactions, collisions, or the capture of rogue planets. Webb's observations provide the first detailed look at these unusual systems, allowing scientists to study the physical and chemical consequences of such dynamics. Each system represents a case study in planetary evolution, revealing processes that are difficult to replicate in simulations without direct observational data. Even in more conventional systems, Webb has refined understanding. Measuring subtle differences in planetary atmospheres across siblings in the same system shows how position and stellar radiation influence chemistry and temperature. Planets closer to the star often have thicker clouds or more ionized atmospheres, while outer planets retain cooler, more stable conditions. These measurements confirm some theoretical predictions while revealing unexpected diversity, emphasizing that planetary evolution is sensitive to both intrinsic and environmental factors. The telescope's sensitivity also uncovers planets in systems previously considered empty. Faint signals in infrared light reveal small or distant planets, showing that planetary systems are often more populated than earlier surveys suggested. Each new detection contributes to statistical studies of planetary occurrence, helping astronomers determine how common different types of planets are in the galaxy. This information guides models of planet formation, suggesting that nature produces a wide variety of outcomes rather than a single, typical planetary system. Unexpected planetary systems also influence thinking about habitability. While extreme orbits and unusual alignments do not preclude life, they complicate assumptions about climate stability, atmospheric retention, and radiation exposure. Webb's ability to measure atmospheric composition across a range of planets informs realistic assessments of conditions that could support life, even under unconventional circumstances. Observations of extreme systems expand the conceptual boundaries for understanding where habitable environments might exist. The diversity revealed by Webb demonstrates that planetary formation is a more flexible and dynamic process than previously appreciated. Interactions between forming planets, residual gas in the protoplanetary disk, and gravitational forces from neighboring stars can all significantly alter outcomes. Observations of multi-planet systems, irregular orbits, and unusual atmospheric compositions provide concrete evidence that theoretical models must accommodate a wide range of possibilities. This reality emphasizes the importance of direct observation in testing and refining predictions. By capturing the details of unexpected planetary systems, Webb bridges gaps between theory and observation. It shows that formation processes can lead to order, chaos, or combinations of both. Planets are not merely passive objects orbiting in simple, stable patterns. They are shaped by complex histories, migrations, and interactions, which Webb reveals with clarity. Each new system observed strengthens understanding, challenges assumptions, and informs models of how planetary systems evolve across the galaxy. Webb's observations provide a unique opportunity to connect phenomena across vastly different scales. On one hand, the telescope examines the smallest details of stars, planets, and dust grains, measuring chemical compositions, temperatures, and motions. On the other hand, it images galaxies, clusters, filaments, and the cosmic web, capturing the organization of matter across billions of light-years. These two perspectives, microscopic and macroscopic, interact in ways that reveal the universe as a cohesive system. Small-scale processes influence large structures, and large-scale structures shape local environments. Webb allows scientists to study both in a single framework. Chemical processes inside stars and planets, for example, have effects that ripple outward. Nuclear fusion in stellar cores produces heavy elements that are later ejected into space through winds or supernova explosions. These elements enrich the surrounding interstellar medium, providing the raw material for new stars, planets, and even organic molecules. Webb can detect the resulting chemical signatures in nebulae and protoplanetary disks, linking the life cycle of individual stars to the formation of planetary systems. Observations of distant galaxies show how these processes scale over millions of stars, revealing patterns of enrichment across entire clusters. Similarly, gravitational dynamics operate on multiple scales simultaneously. The formation of stars within a nebula is influenced by local gravity, but the movement and clustering of galaxies are governed by the gravitational pull of dark matter across vast distances. Webb provides data that traces both levels of influence. By mapping the motions and distributions of galaxies within the cosmic web, scientists see how gravity organizes matter on the largest scales. At the same time, detailed imaging of protostellar regions shows how gravity shapes disks, filaments, and collapsing clouds on much smaller scales. These parallel observations create a coherent picture of matter's behavior throughout the universe. Energy transfer is another connecting factor. Radiation from stars affects the temperature, chemistry, and dynamics of nearby gas clouds. In turn, this influences where new stars form, the composition of planetary atmospheres, and the distribution of matter within galaxies. Webb's spectroscopy allows scientists to measure this radiation and its effects across multiple environments. By studying energy flow from individual stars to entire star-forming regions, researchers link local interactions to broader cosmic phenomena, seeing how micro-level physics manifests at macro scales. The telescope's infrared capability is key in unifying these perspectives. Infrared light penetrates dust, revealing both fine details of planetary systems and the large-scale structures that host them. Observing a protoplanetary disk around a young star and a distant filament of galaxies in the same wavelength range allows scientists to apply similar analytical techniques, comparing chemical abundances, dust distributions, and temperature gradients. This continuity in observation methodology strengthens the connection between small-scale and large-scale astrophysics, making it possible to draw parallels that were previously hidden. Webb also illuminates cycles that operate across scales. Stars form from gas clouds, enrich their surroundings with heavy elements, and influence neighboring regions through radiation and winds. Planets form within these enriched environments, incorporating material produced by previous generations of stars. Galaxies evolve as populations of stars interact, merge, and recycle material. By observing these processes at multiple distances, Webb shows that the same fundamental principles, gravity, radiation, chemistry, govern both individual systems and the large-scale structure of the universe. Micro and macro are not separate. They are interconnected layers of the same cosmic story. The telescope's ability to detect diverse molecules adds another layer of connection. Organic and inorganic compounds observed in protoplanetary disks, stellar nurseries, and galactic environments trace pathways of chemical evolution. Patterns of molecular abundance reveal the effects of local conditions, such as temperature and density, while comparisons across regions show how these processes scale up. For instance, water formation in disks around young stars mirrors larger-scale distributions of oxygen and hydrogen in galaxies, linking planetary chemistry to cosmic chemistry. Webb provides the data needed to make these connections precise and measurable. Understanding dynamic interactions across scales is also crucial. Stellar feedback in the form of winds, radiation, and supernova explosions shapes nearby clouds, influences star formation rates, and contributes to the evolution of entire galaxies. Webb captures these interactions with clarity, measuring the impact of single stars and clusters on their surroundings. At the largest scales, galaxy mergers, filamentary flows, and cluster interactions illustrate analogous processes in gravitational and energetic terms. Observing both small and large interactions highlights universal principles that govern cosmic evolution. The telescope also allows for temporal connections. Observing distant galaxies and early stars shows processes at different times in the universe's history, while studying nearby systems provides a more immediate snapshot. By comparing these epochs, scientists link early chemical enrichment, star formation, and structural assembly to conditions observed in the present-day universe. Microscale processes observed locally can thus be contextualized within the macro-scale history of the cosmos, creating a continuous narrative of evolution over billions of years. Webb's comprehensive data prepares the ground for a holistic understanding of the universe. Individual discoveries, stellar atmospheres, exoplanet chemistry, star formation, galaxy clustering, cosmic filaments, do not exist in isolation. They are connected through common physical and chemical principles. By observing these phenomena consistently and with unprecedented precision, Webb bridges gaps between previously separated domains of astrophysics. Researchers can now approach questions that span from atoms to galaxy clusters, integrating small-scale measurements with large-scale structures into a unified framework. This bridging also has practical implications for scientific modeling. Theories of star formation, planetary evolution, galactic dynamics, and cosmic structure must account for the influence of processes operating at multiple scales simultaneously. Webb provides the evidence needed to test these models rigorously, showing where approximations hold and where detailed observations are necessary. Models can be refined iteratively, using observational constraints from both micro and macro perspectives to achieve a comprehensive, self-consistent understanding. Ultimately, Webb reveals the universe as a network of interconnected processes. Stars, planets, galaxies, and clusters are not isolated phenomena, but parts of a continuum. Chemical evolution, energy transfer, and gravitational dynamics operate at all scales, linking the tiniest dust grains to the largest filaments. By studying these connections, scientists gain both precision and context, understanding how local processes contribute to universal patterns and how cosmic architecture influences small-scale behavior. The discoveries made by Webb are more than data points. They are a story told in light, spanning the universe and time itself. As viewers lie quietly, eyes closed, the vastness of space unfolds gently, measured in photons traveling billions of years. Each observation links to the next, creating a tapestry that bridges the microscopic and the immense, revealing a cosmos both intricate and unified. The universe, in all its vastness, is revealed not as a chaotic expanse, but as a layered, connected system shaped by fundamental laws, evolving gradually, yet full of surprise. Looking back at the earliest galaxies, we see formations that defy simple expectations. Structures of stars, dust, and gas appear mature, their shapes and brightness telling stories of rapid growth. Observing them with Webb, astronomers discern the processes that govern the universe's youth. Gravity collecting matter, stars igniting in dense nurseries, and galaxies interacting in ways both subtle and dramatic. These observations provide a framework for understanding the sequence of cosmic events, illustrating the rhythms of creation and evolution on scales that dwarf human comprehension. Moving closer, Webb examines the environments around nascent stars. Clouds of gas and dust, once opaque and mysterious, are revealed in astonishing detail. Protostars form within filaments and knots, gathering mass from their surroundings. Disks of dust hint at the birthplaces of planets. Infrared light penetrating these dense regions uncovers the dynamics of star formation, showing how gravity, pressure, and chemical reactions intertwine. Each star observed is a node in a vast network, linked to others by shared processes and universal principles. Exoplanets, too, reveal a remarkable diversity. Some orbit in neat alignments reminiscent of our solar system, while others trace eccentric paths or defy conventional predictions entirely. Webb's spectroscopy discloses the composition of their atmospheres, revealing water vapor, carbon dioxide, methane, and other compounds. Each atmosphere is a record of formation and evolution, influenced by stellar radiation, orbital dynamics, and interactions with sibling planets. Observing these worlds expands our understanding of what is possible in planetary systems, stretching the imagination without venturing into fiction. Webb's observations of galaxies provide yet another layer. Beyond individual stars and planets, clusters and filaments form a vast cosmic web. Galaxies are connected, their positions and movements influenced by both visible and unseen matter. Voids punctuate this network, emphasizing the uneven distribution of mass. Infrared imaging allows scientists to detect faint galaxies, to map their positions and interactions, and to trace the flow of matter shaped by gravity and dark matter alike. This structural mapping contextualizes the small-scale processes, revealing the scaffolding upon which stars and planets assemble. Spectroscopy adds chemical and physical depth to this picture. By analyzing light from stars, galaxies, and planetary atmospheres, scientists measure temperatures, elemental abundances, and molecular compositions. Complex molecules, from simple carbon compounds to water, are detected in star-forming regions. These measurements illuminate processes that scale from tiny dust grains to entire galaxies. Webb demonstrates that the same fundamental principles, chemistry, radiation, gravity, operate consistently across immense scales, connecting local and cosmic phenomena. The human element of these discoveries is subtle but profound. Scientists respond to unexpected observations not with disbelief, but with curiosity, patience, and rigor. Surprises refine understanding rather than destabilize it. Each anomaly, each unusual system prompts verification, peer review, and theoretical adjustment. Scientific knowledge grows through iteration, through careful observation and modeling, and through collaboration across continents and disciplines. Webb exemplifies this process, delivering data that is both precise and transformative, fostering a deeper understanding of the universe and our place within it. In examining the cosmos, we also glimpse time itself. Light from distant galaxies and stars is a record of events that occurred billions of years ago. Observing these photons allows scientists to reconstruct sequences of formation, growth, and evolution. Repeated imaging and monitoring provide temporal context, showing changes in stars, galaxies, and planetary atmospheres over time. Webb transforms snapshots into narratives, revealing not only where structures are, but how they have grown and interacted across cosmic epochs. The telescope's contributions create a synthesis of knowledge that is both technical and poetic in its implications. It unites stellar physics, planetary science, galactic dynamics, and cosmology into a coherent framework. Observations at one scale illuminate processes at another. Chemical reactions in protostellar disks connect to planetary atmospheres. Star formation rates in galaxies reflect environmental conditions shaped by cosmic filaments. The universe emerges as a connected system, a web of cause and effect, shaped by forces measurable, observable, and comprehensible through scientific inquiry. For humanity, these discoveries carry perspective. In understanding the mechanics of stars, planets, and galaxies, we understand the processes that eventually led to our own existence. The same cosmic chemistry that forms distant worlds forms our planet. The dynamics that shape remote galaxies once shaped the Milky Way. Webb's insights reinforce the continuity of natural laws, showing that the universe is not a collection of isolated mysteries, but an evolving, interconnected story. Observers of this data are participants in a broader understanding, connected by curiosity and reason to processes that unfold over billions of years. The telescope also exemplifies collaboration on a global scale. Scientists from NASA, ESA, CSA, and other institutions worked together for decades to bring Webb to fruition. Its discoveries result not only from technological achievement, but from the collective effort of researchers, engineers, and observers worldwide. This international collaboration mirrors the interconnectedness revealed in the observations themselves, a human reflection of the cosmic web. Finally, Webb's discoveries are a reminder of patience, persistence, and observation. The universe does not reveal itself instantly. It unfolds gradually, its processes operating over eons, yet with clarity and coherence for those who measure and study carefully. Each photon captured is a clue, each spectrum a record, each image a window into a vast and ordered cosmos. Through meticulous observation, modeling, and synthesis, scientists translate these signals into understanding, revealing a universe that is at once immense, intricate, and accessible to human inquiry. As the mind drifts with this knowledge, a sense of continuity emerges. Webb's data connects the beginning of the universe to its present state, links the smallest molecular processes to galactic evolution, and demonstrates that understanding is built layer by layer, observation by observation. It is a story of connection, precision, and discovery, unfolding quietly in the background of human life, waiting for attentive minds to absorb and reflect upon it. In this sense, the universe is both comprehensible and wondrous, its patterns measurable yet inspiring, its vastness slowly revealed to those who look and wait.